We shall now proceed to analyze a RLC circuit with oscillating electromotive force. Before proceeding to do the analysis of a series RLC circuit, let us consider a simple L and C combination. Let us assume that somehow we have managed to pass a current I equal to I0 cos of omega t plus phi through this combination of L and C. The current flowing through the circuit results in a voltage drop of VL across the inductor, and that results in a charge buildup Q across the plates of the capacitor, which will result in a potential of Vc across the capacitor. VL is given by L times di over dt, and Vc is given by negative of Q divided by C, which is again equal to negative of 1 by C multiplied by negative of integral I dt. So that is equal to 1 by C times integral I dt. That is, voltage across the inductor is VL equal to L times di over dt, and that is equal to negative of I0 omega t sine of omega t plus phi. The voltage across the capacitor is Vc equal to negative of Q by C, that is 1 by C integral I dt. When we do the integration, this will become I0 divided by omega c, then sine of omega t plus phi. We will find the total voltage across the combination, which will be VL plus Vc, and that is equal to negative of omega L minus 1 by omega c multiplied by I0 sine of omega t plus phi. Now let us analyze the dimension of this quantity, that is omega L minus 1 by omega c. On the left hand side we have VL plus Vc, which has the dimension of voltage, and on the right hand side this term has the dimension of current, that is ampere. So obviously this quantity will be having the dimension of resistance, that is ohms. We may combine the inductor and the capacitor to form a single element. So what I am drawing inside this box is a single element, so L and C, whose resistance has a value omega L minus 1 by omega c. Depending upon the value of L and C, this combination will work as an inductor or capacitor. For example, if omega L is greater than 1 by omega c, this will work as an inductor having an equivalent capacitance of L dash. And if omega L is less than 1 by omega c, this combination will work as a capacitor having capacitance omega c dash. So the point that we have to take from the previous discussion is that voltages across the inductor and capacitor are both proportional to sine omega t plus phi, and they are always in phase with each other, or rather exactly out of phase. We now connect a resistance to the LC combination and a AC power supply E0 cos omega t. The current in the circuit satisfies the loop equation L di by dt minus Q by C plus Ri equal to E0 cos omega t. As we have done in all the previous analysis, we can find out the solution for the current by solving this differential equation. But we are not going to do that. Instead, we are going to take a shortcut. That is, we'll consider the solution for the RL circuit and then replace omega L by omega L minus 1 by omega C in the solution. For an RL circuit, we found the solution as IT equal to E0 divided by R square plus omega L the whole square, then cos of omega t plus phi. In this equation, we'll replace omega L by omega L minus 1 by omega C, that is R square plus omega L minus 1 by omega C the whole square, then cos of omega t plus phi. The phase angle in the case of a RL circuit was tan phi equal to minus omega L divided by R. So this is the case of a RL circuit. Therefore, in the case of an RLC circuit, tan phi equal to 1 by omega C minus omega L divided by R, that is equal to 1 by R omega C minus omega L divided by R. The previous expressions were derived for the case omega L greater than 1 by omega C and the circuit behaves like a equivalent inductor having inductance L dash, and that is equal to omega L minus 1 by omega C. But these expressions are also correct if 1 by omega C greater than omega L and the circuit behaves like a equivalent capacitance C dash, so that omega C dash equal to 1 by omega C minus omega L. A series RLC circuit exhibits the phenomenon of resonance, and we will try to understand the resonance phenomenon that is exhibited by RLC circuit. The current in a series RLC circuit is given by IT equal to E0 over square root of R square plus omega L minus 1 by omega C the whole square multiplied by cos of omega t plus phi. And this equation tells us that we get the greatest current when the driving frequency omega is such that omega L minus 1 by omega C equal to 0. That is omega L equal to 1 by omega C and then omega square equal to 1 by LC, or omega equal to omega 0 equal to square root of 1 by LC, where omega 0 is known as the resonant frequency of the undamped LC circuit. At resonance, omega L is equal to 1 by omega C and this term becomes equal to 0. In that case, the current reduces to IT equal to E0 cos omega t divided by R, and that is exactly the current that would flow if the circuit contains only the resistance. At resonance, the voltages across the inductor and capacitor are always equal and opposite, so that they cancel, and therefore the current oscillations have the natural frequency omega 0 equal to 1 by square root of LC. To understand the effect of resistance in the resonance that is exhibited by the RLC circuit, let us consider this simple case. We are going to consider a circuit containing an inductor having L equal to 10 raised to minus 4 Henry, and the capacitance included in the circuit is C equal to 10 raised to minus 8 Farad. The resistance connected is R, and we are going to vary the value of R and then going to see how the resonance curves change. So on the x-axis we have omega over omega 0, and on the y-axis we have the current in amperes, and the input voltage has a magnitude of 100 volts. When the value of the resistance is very low, that is when R equal to 20 ohms, the current oscillations have the maximum amplitude. The resonance occurs at omega equal to omega 0. As we increase the value of R to 60 ohms, we can see that damping in the circuit increases, and then the amplitude of the current oscillations decreases. As we again increase the value of R to 200 ohms, we can see that the amplitude is very low. Even though the amplitude is low, the peak of the oscillations occurs exactly at omega 0. We shall now try to find out an expression for the width of the resonance curve. We'll indicate the width of the resonance curve as 2 times delta omega, and then we'll try to relate that mathematically to the Q of the circuit. Let us assume that our circuit is resonating at omega 0. We'll consider a point in the neighborhood of omega 0, which is located at omega equal to omega 0 plus delta omega. So this width is delta omega, and the entire width, that means that this width is 2 times delta omega. The Q factor of the circuit is given by omega 0 L divided by R. And in general, if the Q factor is high, the resonance curve will be narrow and high at omega 0. The width of the resonance curve in general depends on the Q factor of the circuit, that is given by omega 0 L divided by R. We have the current in the RLC circuit as given by IT equal to E0 divided by square root of R square plus omega L minus 1 by omega C the whole square cos omega t plus phi. At resonance, omega L equal to 1 by omega C, and then we have IT equal to E0 divided by R, then cos of omega t plus phi. This is equation 1 and this is equation 2. At omega equal to omega 0 plus delta omega, that is if this is the resonance curve, this is omega 0, and this point, this is omega 0 plus delta omega. The denominator in the square root for the current expression 1 can be written as omega L minus 1 by omega C equal to omega 0 plus delta omega. So instead of omega, we have substituted omega 0 plus delta omega multiplied by L minus 1 by omega 0 plus delta omega multiplied by C. This is equal to omega 0 multiplied by L multiplied by 1 plus delta omega divided by omega 0 minus 1 over omega 0 C, then 1 plus delta omega divided by omega 0. And this is equal to omega 0 L multiplied by 1 plus delta omega divided by omega 0 minus 1 divided by omega 0 square multiplied by LC, then 1 plus delta omega divided by omega 0. That is, we have taken omega 0 L as common from the two terms. But we have omega 0 equal to 1 by square root of LC, and therefore this term cancels, resulting in the expression omega 0 L multiplied by 1 plus delta omega divided by omega 0 minus 1 over 1 plus delta omega divided by omega 0. We may now have to use the approximation 1 over 1 plus epsilon approximately equal to 1 minus epsilon, and write omega L minus 1 by omega c as equal to omega 0 L multiplied by 1 plus delta omega divided by omega 0 minus 1 minus delta omega divided by omega 0, and this is equal to omega 0 L multiplied by 2 times delta omega divided by omega 0 upon simplification. When omega is shifted from resonance, that is when omega, so this is omega 0 at resonance, let us consider this point. So when omega is shifted from resonance, and also when modulus of omega L minus 1 by omega c is equal to R, when these two conditions are satisfied, we can write omega L minus 1 by omega c equal to R, and that is equal to omega 0 L multiplied by 2 times delta omega mod divided by omega 0. From where we can write 2 times delta omega divided by omega 0 equal to R divided by omega 0 L, which is equal to 1 over Q. Equation 4 connects the width of the resonance curve, that is 2 delta omega, to the Q of the circuit, that is 2 delta omega divided by omega 0, this is equal to 1 over Q. So this width is 2 times delta omega. When the condition mod omega L minus 1 by omega c equal to R is satisfied, we have derived the expression mod delta omega by omega 0 equal to 1 by 2q. We shall now find out the amplitude of current at this particular point. So this is omega 0 and this is omega equal to omega 0 plus delta omega. And what would be the amplitude of the current at this point? So this is current, instantaneous current. And what would be the amplitude of current at this particular point? Let us call this as I dash t. I dash t equal to E0 divided by square root of 2r square, then cos of omega t plus phi, that is equal to 1 over square root of 2 times E0 divided by r cos of omega t plus phi, which is nothing but 1 over square root of 2 multiplied by it. That is, the current amplitude will have fallen 1 by root 2 times the peak when mod delta omega by omega 0 equal to 2q. That is, I dash t equal to 1 by square root of 2 times it. Now the fall of current amplitude to 1 by square root of times is shown in this figure when delta omega by omega 0 is equal to 2q. These 2 points, that is this point and this point, because the energy or power is proportional to the amplitude squared. Often we express the width of a resonance peak by giving the full width, and the full width is mathematically defined to be 2 times delta omega, and width 2 times delta omega is equal to omega 0 multiplied by 1 by q. Now this figure shows a plot between omega by omega 0 and phase angle phi. The phase angle is expressed as tan phi equal to 1 by r omega c minus omega l divided by r. Let us take a typical case where r has been taken to be 20 ohms. At very low frequency, capacitor is the dominant hindrance to current flow and phi is positive. So this is that case. At low frequencies, phi is positive, and at resonance, phi becomes equal to 0. So this is that point at the center. At the center, phi equal to 0. And then as frequency increases from omega 0, this is the point omega equal to omega 0. Phi shifts from positive to negative angles. The second plot has R equal to 60 ohms, where we can see that the variation follows a similar trend. As we increase the value of R to 200 ohms, the curve becomes like this. We notice that when R is very low, that is when Q is very high, the phase angle goes to negative values more abruptly. And with that, we conclude our study on series RLC circuit to which a sinusoidal voltage is applied.